All right, for these first couple of problems, these are kind of weird. It says determine whether the function is a solution of the differential equation x times y prime equal minus 2y equals x cubed times e to the x. So I left my answer here just because I didn't want to rewrite it. But how do you check whether a function is a solution? So if this is a solution, I should be able to plug in x squared in place of y and have the two sides be equal. So remember, y prime is just dy dx. So y prime is 2x. So I should be able to sub in values. So x times, instead of y prime, I'm going to sub in 2x. Minus 2 times, instead of y, I'm going to sub in x squared. Is that equal to x cubed times e to the x? So this one is, this should say, 2x squared times, or minus 2x squared, is that equal to x cubed times e to the x? I thought I had an x cubed over here. Let me check my work on that, or did I just write something wrong? Oops, I just wrote something wrong. Okay, anyway, so this is like, does 0 equal x cubed times e to the x always? No, these two sides are only equal if x is equal to 0. So the equation has to be true for all x, all real numbers. So even though it's sometimes true, not always. So the same thing happens with this one. This is, okay, y prime would equal 3x squared. So subbing into this equation, it would be x times y prime minus 2 times y is equal to x cubed e to the x. So same thing, 3x cubed minus 2x cubed is not equal to e to the x times x cubed. It's equal to 1 times x cubed. But that's only true, again, for x equals 0. Okay, so not true for all real x. So no, that's not a solution to the differential equation. For the next one, some curves corresponding to different values of c in the general solution of the differential equation are given. So think slope fields here. That's a visual representation of that. Find the particular solution that passes through the point on the graph. So here's the point they give me. They give me both the solution and the differential equation, so I don't have to worry about separate, integrate, celebrate, any of that stuff. I'm just saying, okay, find the solution when you plug in 0 for x and 3 for y. So using this solution, it should be 3 equals c times e to the 0. So 3 equals c, right? Because e to the 0 is 1. So the particular solution is y equals 3 e to the negative x over 2. They did all the hard work for us on that one. All right, matching for the next section. Match the differential equation with its slope field. So remember, you don't have to spend time separate, integrate, celebrating over here. You're just thinking, which out of all of these, which ones look like the graph? Like, you should know that a sine graph generally looks like this, right? And a cosine graph generally looks like this, because these don't have any horizontal shifts in them, right? So I'm just trying to match those up right off the bat. So see how C has this odd function thing happening, like a sine graph, whereas D has sort of the even symmetry happening. So that's the cosine graph. So that's how I decided that 57 was C and 58 was B. That leaves A and D. Okay, so take a look at 0. I like to use the x equals 0 to see what's happening here. So when x equals 0, number 60 is undefined, which looks like that's what's happening here. There are either vertical tangents sketched in, or they just don't have anything. And then versus D, at 0, there's clearly a positive slope there. So 60 has to be A, which leaves us with D for this one. But again, e to the negative 2x, that looks like an e to the x graph that's been reflected. And yeah, so we can kind of see that curvature here. Now this, to me, these look like negative e to the x graphs, but again, depending on what we're looking at, we're just looking between negative 3 over 2 and 3 over 2. So yeah, so I think the curvature there is okay. The point is, you don't want to spend a bunch of time thinking of what is the solution, what is the y equals. You could do that, but you might mess up doing that, where it's easier just to say, do these graphs match up and do some of the points fit in. For number 65, it says use the slope field. Excuse me. Use the slope field for the differential equation y prime equals 1 over x. So dy dx equals 1 over x, where x is greater than 0, to sketch the graph of the solution. So, I guess I meant to erase this. Start this over. Okay, so sketch through the graph and then make a conjecture about the behavior of a particular solution of y prime equals 1 over x as x approaches infinity. So first, let's just sketch the thing. Don't overthink it. Plot the point they give you. So here's the point 1, 0. Use the little slopes to help guide your line. So it doesn't have to be perfect. It's like, well, how do I know that I'm here instead of up here? Just let the little tangent slopes guide you. They're just looking on this that you don't put arrows on the ends because we don't know what happens outside of this slope field. And I guess mine is curving a bit strangely, but let me just do something like this. So you're just trying to fit a general curve there. They're not going to say, oh, it's supposed to go through this tangent line or whatever. They just want you to follow a decent curve. And then for the other one, plot the point to -1. So that's like right here. And again, use that to kind of guide you through something like that. All right, what about the other part? So it said, make a conjecture about the behavior of the particular solution as x approaches infinity. So they want us to find the limit as x approaches infinity of y. So it's our job to figure out what the equation for y is if dy dx is 1 over x. So this is where we separate. So I'm going to multiply dx over to this side. Then we integrate. So this is, not natural log, sorry. Y equals the natural log of the absolute value of x plus c. We separate, integrate, celebrate. Now find the particular solution. So for the first one, 1, 0 is on, it's on dy dx, but if that point is on dy dx, if we know that point is on there, then we know it's also on the graph of y, right? Because remember, this is the particular solution. This is the y equals. This looks like a natural log graph, and this is the point that it goes through. We're just saying we're evaluating dy dx at 1, 0 for sure. Okay, so that means I should be putting in 0 for y and 1 for x and solving for c. You need to know that natural log of 1 is 0. Some of you didn't simplify that on our chapter 5 test, so it is important. You need to know what that is. So c is just 0, so y equals natural log absolute value of x. And then we were asked to make a conjecture about the limit as x approaches infinity of the natural log of x. That's the natural log of infinity, which is just infinity. We can see that in the graph. Remember, natural log graphs will continue to increase just at a very slow rate. So same equation, but now we're looking at the point to -1. So go back to this y equals. So -1 equals the natural log of 2 plus c. And so this c value would just be natural log of 2 minus 1, or -1 plus natural log of 2. It doesn't matter. So this particular solution is y equals natural log of x plus natural log of 2 minus 1. You can work on condensing this if you want, but that's not necessary. The limit as x approaches infinity of natural log of x plus natural log of 2 minus 1 is infinity plus natural log of 2 minus 1. Remember, infinity plus a constant is just infinity. So same conjecture. This blue graph also grows without bound, just very slowly. Same idea for number 66. So now the differential equation is 1 over y. So I plotted the point 0, 1 and just kind of sketched in where I thought this could fit. And I plotted the point 1, 1 and did the same thing. Remember not to put arrows and not to go past the slope field. We don't know what happens outside of this little square. Okay, so dy dx equals 1 over y. So you're going to multiply y over to the dy side, and then you'll just be left with 1 dx on the right side. Integrate y, you get y squared over 2, and that equals x plus c. I just like to plug in the initial condition from here, and then I'll work on stuff. If you multiply by 2 right now, it would be y squared equals 2x, still plus c. It wouldn't be plus 2c. So that's why I don't like to mess with that. All right, so the point 0, 1 is on y. So that means that we can put in 1 for y and 0 for x. So I get c equals 1/2. So it's y squared over 2 equals x plus 1/2. You want to solve for y, so multiply by 2. Now y squared equals 2x plus 1. Normally when we square root both sides of an equation, we get plus or minus the square root of 2x plus 1, except in this problem, we're told two things. They flat out tell us y is greater than 0, but they don't always tell you that. So how do you know that it's positive? You use your slope field and you look and see that all of these y values that we're plugging in here, all of them are positive. So on this graph here, the only possible y values are positive square root of 2x plus 1. And then finally, the limit as x approaches infinity of the square root of 2x plus 1 is equal to, get that out of there, sorry, 2x plus 1 is equal to infinity as well. For the other one, the 0.11 is on y, so we can plug in 1 for y and 1 for x. 1/2 minus 1 is negative 1/2 for c. And then go back to the equation y squared over 2 equals x minus 1/2. Multiply by 2. Y squared equals 2x minus 1. It's still true that y is positive on this blue curve as well. So y equals the square root of 2x minus 1. And finally, my conjecture about the limit as x approaches infinity is that of this graph is that it's equal to infinity. All right, now I did not erase all of this because I did not want to write this out again. You will not have 10 steps to do on my quiz or test or on the AP exam, so this was a bit excessive. But what was good about doing 10 steps, assuming you at least wrote out what they would all be, it should be tattooed into your brain now, the setup of Euler's method. And I can always tell who took the time to write this out or not, because every year it'll be like, wait, what's Euler's method again? And I understand not remembering it, but if you took the time to write this out every single time, then you should be pretty good. So what is Euler's method? You take a step. This says step size is 0.1. You're starting at 0. So start at 0, 2. So I'm going to take one little step up to find y of 0.1. So I start at the beginning point, y of 0, add the slope at 0 times the step size. That's your formula every single time. And then whenever you get for this, don't round the answer. Then I want to take another step of 0.1. So from 0.1, add 0.1 to that, you're at y of 0.2. So now you're on the previous point, y of 0.1, plus y prime of 0.1 times the little step size that you're taking. So see how it's a pattern? These two values should match. And then how do you find y prime of 0.1 or 0.2 or whatever? It says here, y prime is equal to the x coordinate plus the y coordinate. So y prime of 0, nice and easy, 0 plus 2, 2. And then as the numbers get more complicated, you're just continuing to add. When I do this on my calculator, so let me start here. So y of 0.1 was 11 fifths. You can see I got tired of doing this without a calculator. 23 tenths times 0.1. Okay, I got this for y2. Now, if I want to find y3, the reason I wrote all of this out, but on my calculator, I'm doing, okay, this is y of 0.2. So it's y of 0.2 plus the slope at y of 0.2. Now, the slope at y of 0.2 is that answer, the y plus the x, and then times 0.1. And then I can just keep going with that, right? Or you could also do this. So this is my new answer, right? 2.693. Let's find the next slope. So the next slope would be, Well, no, let's just keep going. So it's that plus that answer plus what's the x value that I'm evaluating at here? 0.3. You need to write it out because I would lose track if I didn't have it written down, times the step size, 2.9923, right? So anyway, so you can kind of shortcut things like that. You usually have to do 2 or maybe 3 steps, maybe 4 at the most on the AP exam. 10 is a bit much. For the same reason of just this being overkill, I cut problems 75 and 76 from our assignment. 75 is another like, hey, you do this in 10 steps. 76, I think, was 4 or 5 steps. If you want more practice on this, by all means, do 75 and 76. I can get you those answers. Just let me know. Otherwise, I'm going to skip on to this section. So we're kind of doing the same thing, just not as many steps. So I did not erase my work here because, again, I'm just going to talk through it. Complete the table using the exact solution of the differential equation and 2 approximations obtained using Euler's method to approximate the particular solution of the differential equation. Use delta x or h equals 0.2 and 0.1 to compute each approximation to 4 decimal places. Okay, so the first part, the exact solution, this is just me typing into my calculator. You know, when I put in 0, 3 times e to the 0 is 3. And then when I put in 0.2, 3 times e to the 0.2 is this. And then I rounded to 4 places. And then I just kept doing that. Second enter, make that 0.4. Okay, so that's pretty easy. That's the exact thing. Now, what about the step size one? So you're still starting at 3. Let me split screen here. We're still starting at 3. Again, it's silly not to write this out because it's easy to mix up numbers here. So if I want to find y of 0.2, I'm going to start at y of 0, add y prime of 0 to that, and multiply by the step size 0.2. And here's the nice thing. dy dx this time is just equal to y. So when I do this, y of 0 is 3, y prime of 0 is also 3, because it's the y coordinate there, times 0.2. And then I just kept doing that. So let's say now I want to find y of 0.4. So that's y of 0.2, which is 3.6, plus the slope at 0.2, which is still just the y coordinate, 3.6, times the step size, 0.2. And then I just kept doing the same thing. So the next one is going to be that answer plus that answer times 0.2. If your calculator lets you go up and grab the line before, this turns out to be pretty nice. If it doesn't, then yeah, you have a little bit of typing to do. And so I just kept doing that. The next one is going to be that answer plus that answer times 0.2. So this was my solution for, just let me scroll. There we go. My solution for y of 0.8. Oh no, y of up here. Yeah, y of 0.8. And then the last one, y of 1, is, there we go, that answer plus that answer times 0.2. Do not round as you go. I guess this is okay because it kept it to 4 places. But if I had to find one beyond this, don't round this to 4 places. It'll start throwing you off. You're only allowed to round your final answers. And you can see I did that here. We have more steps to take if the step size is only 0.1. They still want us to start at 0 and ultimately find y of 0.2. So to do that, you're going to have to take 2 steps. Now, I didn't show all of my work again, but here it was again. So now plug in 0.1. So first predict y of 0.1, So y of 0.1 should equal y of 0 plus the slope at 0 times 0.1. That's y of 0.1. Now take another 0.1 step to get y of 0.2, which is the answer they want. So that answer plus the slope at that answer times 0.1. Now I'm going to find y of 0.3. That answer plus the slope at that answer times 0.1. And you just keep doing that. So see how as I kept doing that, I didn't round. I get past 4 decimal places in the next round. I didn't round until the very end. So I found all these values, and then I went back and wrote underneath them, okay, but y of 0.6 is this, y of 0.8 is this, y of 1 is this. The true or false section I thought was pretty tricky. it kind of seems like they're all true at first. So let's talk about this. So 89 says if y equals f of x is a solution of a first order differential equation, that just means a dy dx instead of like a second derivative or third or whatever, then y equals f of x plus c is also a solution. So we have to be careful here because if y equals f of x is a solution, that means that the c value is plus 0. So if that works, that's a particular solution they're talking about because they didn't start off with the plus c. Then no, all of the other general solutions will not be a solution. It's just this specific one. There's an example in the back of the book that says uses something specific. I don't think that I would have thought to use the example they used in the back of the book. I think it was like, I have it somewhere. It was like, what if y is equal to like 3x squared or something? It was something like this, and they came up with a dy dx where that didn't work. But I just think in general, this is a particular solution because they assigned a c value of 0. So that means there are no other solutions. That is the solution. 90 is true. The general solution of a differential equation is this quadratic. To find a particular solution, you must be given two initial conditions. Yeah, because you would need to know, you need to plug in an x value and a y value to find the constant c. And then you would need a different one to also find the variable in front of x. So yeah, there are two unknowns there. That's sort of like when they give you an acceleration equation to start off with, and then they give you some value of velocity and some value of position to get to the final position function. 91, we had this at the top of our notes. What are slope fields? They are the general solutions of differential equations. They show you all of the vertical shift possibilities for what your y equals will be. And then 92 is false because even though this point works, it says a slope field shows that the slope at point 11 is 6. This slope field represents the family of solutions for the differential equation y prime equals 4x plus 2y. So yes, this works. 4 plus 2 is 6. But that's just one possibility. It doesn't mean that that's the only one. So again, on 89 and 92, I don't think that the phrasing is clear that they mean that's the only family of solutions for the differential equation. But checking with the back of the book, I think that's sort of what they're indicating. So I think that our AP problems are a little more explicit than that. But we'll just have to kind of be careful about those. All right, come into office hours if you have any questions, please.